This last problem is a bit of a challenge. We've got a cylindrical tank that's lying on its side, and we have to pump all the water out. And so the trick to this one really is knowing how to set the thing up. What you want to do on this one is I'm going to draw in a slice. Let's see, here is the center of my tank. I'm going to draw a slice in the lower half. So here's my slice of water. And working out the area of this slice of water is a little bit involved. But there's our slice. And here's what you want to do. You want to draw in some lines here and here in order to work things out. And this is going to be my X. Normally we've let X be the depth of the strip. In this case, letting X be that length from the center of the thing to X is going to make things easier for us later on. So if we look at this, at the end of the tank, we've got, I'm just going to draw it as a cross section. Let me try that again. My circle there was so bad that it thought I was trying to draw an ellipse. All right, so here at the end of the tank, we've got this sort of thing going on. We know this length is 1, this length is 1, this length is X, and I'm going to call this H here, just for half. So let's work out what this is. By the Pythagorean theorem, x squared plus h squared is 1. So h squared is 1 minus x squared. So h is square root of 1 minus x squared. All right. So now we need to work out the area of this thing. Well, h is 1/2 of the width. So for this slice here, the area is 2h times 10. Yeah, 10 was the length of the thing. So 2h times 10, so 20h. And if you want to put that in terms of x, which we need to do, that's going to be 20 times square root of 1 minus x squared. So the volume is going to be that times dx. And the weight of the slice is going to be that multiplied by 9,800. So let's see, 9,800 times 20 gives me 196,000 times square root of 1 plus x squared, or I'm sorry, 1 minus x squared dx. And what about the distance? The distance that this thing needs to be lifted is, this might be a little tricky. The distance is going to be from here down to there plus x. So the distance is going to be 1 plus x. And notice that works for slices that are above or below the center. A slice that's dead on in the middle has to be lifted by the radius, which is 1. Down here, this is going to be 1 plus x. If we had something that was up here, then x would be a negative value. So maybe I should write that over here. If we think of this as being sort of an x-axis, we've got x is negative up here and x is positive down here. So that's the distance. So the volume, or rather the work, is going to be the integral of 196,000 times 1 plus x, the square root of 1 minus x squared dx, from -1 to 1. All right. So yeah, that's the force times the distance, and the x values at the top, x is -1, at the bottom, x is 1. So that's what we get for our work integral. Now I'm gonna rewrite this slightly. I'm just gonna pull the 196,000 out front. Like that. Now, how could we do this integral? Well, the quick answer is we could plug it into Desmos and have it do it for us. And I actually want to do that, and I want to show you another slick way of doing this integral. I mean, you know, if this were a thing where somebody were paying me to find the answer, that's what I would do, is stick it into Desmos or Wolfram Alpha or something. So let's do it on Desmos. Let's see, we've got 196,000 times the integral from -1 to 1 of 1 plus x times square root of 1 minus x squared dx. And it gives me an answer of 307,000 something. And this is a big number, so I'm going to feel perfectly justified in just rounding it to the nearest whole number. And we're dealing in meters here, so this is in joules. So 300,876 joules. And I want to just double check something real quick. Yeah, all right. So that's getting the computer to do it for us. If we had to do this integral ourselves, what we'd need to do would be break it up into two integrals. Let me bring it up here where you can actually see it. I'm going to distribute this, this radical across the 1 plus x squared. When I do that, we get square root of 1 minus x squared, and then plus x times 1 minus x squared dx. So we've got to integrate these two things. Now, the second one, well, we've got two integrals, and I'm going to break this into two different integrals. Instead of having two parts to an integral, I'm going to slide this down, put a dx there, and then plus integral from -1 to 1 of that. And then we've still got to have that 196,000 on the front times both of them. Now, it turns out these two integrals, if we think about them, we can do them easily. This thing right here is an odd function. And what I mean by that is it's symmetry. Let's look at it on Desmos. If we were to graph that, if we were to just graph y equals x times 1 minus x squared. Oh wait, there's supposed to be a square root. If you look at that and you go from -1 to 1, notice the area of one part of it is going to completely cancel the area of the other one out. So thanks to that, we know that this evaluates to 0. Now, what about the other one, square root of 1 minus x squared? Well, that's a semicircle. You come over here and graph it. Y equals square root of 1 minus x squared. That's a semicircle, and its area, we can figure out, we can integrate that by geometry. So this integral is telling us to find the area of a semicircle. With a radius of 1. So what we get here is 196,000 And the area of a semicircle with radius 1 is 1/2 times pi times 1 squared. So let's see, 196,000 over 2. That's 98,000 pi. So that's our exact answer there of 98,000 pi. And I guess we need units on there, 98,000 pi joules. And if you go in and look at them, this up here is equal to this here. 98,000 pi is 307,876. So anyway, that's the last example I want to do from this section. Take a look at the homework problems and let me know if you have questions.